Happy Thanksgiving, my little turkeys. So we are going to focus on molecular geometry today. I was really proud of you guys when you did your POGIL, and I think that introduced the concept of molecular geometry a lot. So I don't think that there's a lot of new stuff that we're going to have to cover in this video. I think that it'll just help to kind of go over some of that information that was in your POGIL. Also, when you are watching this video, look at the slides the PowerPoint slides that I passed out to you in class. There were 9 slides of them, and if you lost those or if you just want to print out a new copy because some of those pictures on the slides that I gave you were pretty small, please feel free to do so if you're having a hard time seeing those. So first I just want to start off with that very first slide on that PowerPoint, so we'll just kind of work our way through, okay? Now, we've already talked about before that Lewis structures tell us which atoms are bonded together. So a Lewis structure can tell me what's the central atom. It can also tell me that central atom must be the least electronegative. It can also tell me how the electrons are distributed around these atoms, because we can check to make sure that all of the atoms have a formal charge of 0, and specifically we care about that central atom having that formal charge of 0. So Lewis structures can tell us what's bonded to the central atom, how many things are bonded to the central atom, and are there any lone pairs of electrons that are around a central atom. Okay? Now, this doesn't tell us, though, a Lewis structure can't tell us the shape that a molecule is going to make. So molecular geometry can tell us that. So that's why we're going to focus on this. In terms of the overall shape, it's going to be determined by a bond angle. Now, that just means that you saw in your POGIL that if you have 2 pairs of electrons, those 2 pairs of electrons, they both have the same charge. They're both negatively charged. So that means that they're going to repel one another because they're similarly charged. So if they're similarly charged and they start to repel, it's really the angle that's going to determine the shape. And because of the angle, we have given names of shapes for these different types of molecules. Now, bond angles are determined by something called VSEPR theory, which VSEPR theory we'll talk about in just a second. But all this means is bond angles are determined by the amount of repulsion between electrons. That's it. So these electrons are repelling one another. They want to push far away from one another. So because they're repelling, the amount that they repel is going to determine the angle at which these other atoms are going to be surrounding the central atom. Now, VSEPR theory, VSEPR stands for valence shell, electron pair, repulsion. So valence shell, electron pair, repulsion. All of this it's just one big word to explain that the valence shell electrons, the outermost electrons, they're the ones that are doing the bonding. You've already known that. So valence shell electrons are the ones doing the bonding. We have pairs of electrons always, right? Because in a bond, it's a pair of electrons. If there are extra electrons that are surrounding the central atom, they always happen in pairs. So that's this electron pair. And repulsion, meaning that these electron pairs are going to repel one another because they have the exact same charge. And 2 alike things, they're going to bump heads, they're going to repel. So they don't want to attract one another, they're going to repel. So valence shell, electron pair, repulsion. That's what VSEPR stands for. And it's saying the exact same thing that we just said. It is saying that a shape of a molecule, or the shape of the molecule, will happen because of electron pairs repelling each other. That's it. That's all this means. Okay, so electrons repel. They try to get as far away from each other as possible. Okay, we're going to first just explore electron domains. Now, we know that there can be up to, or we've seen or observed, up to 6 electron domains. Now, when you started to work on your POGIL, you had to try to discover what an electron domain was. So in your POGIL, you guys figured out that an electron domain is how many bonded or non-bonded electron pairs were around the central atom. So that's an electron domain. How many electrons do I have as pairs around that central atom? So that's an electron domain. It says we will first explore the molecular form ABN. All that means is we have, and actually let me give you some examples using our board here. So a molecular form ABN, that's just like a real generic form for a molecular compound. So instead of saying CH4, that's the same thing. This is just a very generic form. So this N is just telling me the number of how many of these surrounding atoms I'm going to have. And then A typically just stands for the central atom. So if I looked at this, C would be my central atom, and then I'd have 4 H's surrounding that central atom. If I look at NH3, this A, which in this case would be N, tells me this is my central atom. And then the B represents the surrounding atoms, what are around it. So I have hydrogen around this nitrogen. How many do I have? So N stands for number. How many of those do I have? Well, I have 3. I have 3 hydrogen surrounding that central atom. So that's what this just very generic form ABN stands for. Okay. Let's go back. Okay. So always when we pick out or trying to figure out the molecular geometry, we always have to determine how many electron domains are around the central atom. How many electron domains are around the central atom? So that's imperative that you have to know how to pick out an electron domain. And you were doing that in your POGIL. So remember when we did NH3, well, we had nitrogen. If I gave you the Lewis structure, it looked like that. So if I asked you how many electron domains does NH3 have, you would tell me that there should be 4. 1, 2, 3, 4. So I have 4 domains here. How many bonding domains do I have, and how many non-bonding domains do I have? So if I look at this, I see that I have 1, 2, 3 bonding domains, and then I have 1 lone pair, which would be my non-bonding domain. So in this I have 4 electron domains. 3 are bonding, 1 is non-bonding. If we looked at another example, if we had CH4, we have carbon, and then I have H's all around. So carbon is my central atom. In terms of an electron domain, let me ask you this. Do we ever look at the surrounding atom? You should be telling me no. So electron domains are only about the central atom. So if I look at this, I have how many electron domains around that central atom? Again, in this case, there would be 4. I have 1 here, 1 here, 1 here, 1 there. So there are 4 electron domains in this one, and they're all bonding. So in this one, I have 4 bonding electron domains. Okay, so I think we're good on being able to pick out electron domains. So in terms of electron domains, you already know that's the region of electrons that are either bonded or non-bonded to that central atom. It has to be bonded to the central atom, okay? That's super important that it's just for the central atom. So electron domain, where am I going to find these electrons? Around the central atom. They could be bonded, they could be non-bonded. We just have to figure that out. Okay, so in terms of electron domain geometry, this is different than the molecular geometry. So these electron domain geometries are just telling us that we have 5 major categories. So there are 5 different electron domain geometries. If there are 2 electron domains, then it's linear. If there are 3 electron domains, then the overall geometry would be called trigonal planar. If there are 4 electron domains, the overall electron domain geometry would be tetrahedral. If there are 5 electron domains, it would be called trigonal bipyramidal. And if there are 6 electron domains, then we would call that octahedral. So these are the 5 major categories or 5 major geometries. And these are 4 electron domain geometries. What I want you to know is that once you get to this step, you're going to have to take another step to figure out the molecular geometry, because there are subcategories in each one of these, okay? So these are the 5 major types of electron domain geometries: linear, trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral. And they're all based on their electron domains. So if it's 2 electron domains, linear. If it's 3 electron domains, the overall electron domain geometry is trigonal planar. 4 electron domains is tetrahedral. 5 electron domains is trigonal bipyramidal. And 6 electron domains is octahedral. Okay? What would I do, though, if I have 3 electron domains and I have 2 bonding and 1 lone pair? So that's where these major categories kind of fail us. So that's where molecular geometry comes into play. These are just the shapes, guys, too, of the electron domain geometry ones. So if we look here, number of electron domains, 2. So I have 2 things, 2 electron domains around that central atom. So that would be like, BeF2. Be would be my central atom. F on this side, F on this side. Okay, so here would be a really good example of a linear type of electron domain geometry. I have 2 electron domains around that central atom. So then that means since I have 2 electron domains, then the electron domain geometry is linear. And it looks linear, right? So that's just a good example. Okay, so here's a shape for linear. We can see here that the bond angle for linear is 180 degrees, which it makes sense because it's linear. So linear will have a bond angle of 180 degrees. On the next one, if it has 3 electron domains, we just said that that was trigonal planar. So here's what it would look like if it were trigonal planar. So that's the shape that it would take. And the angle between the surrounding atoms would be 120. So if I see all of these, those angles would be 120. If there are 4 electron domains, then I have tetrahedral. And if I'm looking at this tetrahedral, then the bond angle between the surrounding atoms would be 109.5. You do need to know these bond angles because I will ask you those. On this one over here, guys, we have number of electron domains if we had 5. If we have 5 electron domains, we call that trigonal bipyramidal. So if there are 5 electron domains, that shape is going to be trigonal bipyramidal. In terms of the bond angle, it would show 120 degrees as well as 90 degrees. And the reason is some of these are going to end up being perpendicular to one another. Some of the surrounding atoms are. But other of the surrounding atoms, the ones that are in here, are 120 degrees to one another. So it's like it's... Sorry, guys. So we have 120 degrees here, and then the 90 degrees here. So it actually has 2 different angles in that one. Guys, the last one is the one that has 6 electron domains, and that's called octahedral, which, if it has 6, you know, octa means 8, so I don't really know why I call it octahedral. But anyway, 6 electron domains, it's called octahedral, and if we look, there's 90 degrees between surrounding atoms. Now, like we said, this is just a very major category. So the electron domain geometry can just tell me how many electron domains